2 needs to be? No. The alpha 2 needs to be positive. Because if this error term is positive, it means x2 is too low relative to its equilibrium value. So for the positive error to reduce, x2 needs to rise. And so this alpha 2 needs to be positive. Okay? So if x1 is doing the error correction, alpha 1 should be negative and significant. If x2 is doing the error correction, alpha 2 should be positive and significant. And in general, both could be significant. Okay, so now also the magnitude. So if x1 is error correcting, the magnitude of alpha 1 measures the proportion of the deviation that is corrected each period. So alpha 1 equal to minus 0.4, that means 40% of the error is being eliminated, is being corrected each period. Okay? Using a similar logic, we just saw that alpha 2 needs to be positive if x2 is doing the error correction. Okay? Is this clear? Okay, good. So here's a small illustration of how this error correction works. Okay, so simple model for two co-integrated variables. So this is the error correction model. These terms are not there. So this gamma matrix is 0. So we only have this part. So alpha 1 is negative 0.2. That means x1 corrects 20% of the error in one period. And x2, the coefficient of x2 is also significant. So x2 corrects 10% of the error each period. Okay, so these are the co-integrated variables, x1 and x2. So just by looking at them, you can see x1, x2 individually. They are very volatile and seem to be non-stationary, but the difference between them seems rather stationary with a mean of 0. Okay, so they are co-integrated with each other. Now, here, because these numbers are relatively small, so the deviation, that means the error correction each period, is not particularly rapid. It's not very fast. Okay, 20% here, 10% here. So because of that, the linear combination, it is stationary but relatively persistent. So that illustrates this relatively slow error correction. Okay, and here in graph C, they show the speed of adjustment if you hit this linear combination with a large shock, and then you see what happens to this large shock. So the system is in equilibrium at time 50. There's a huge shock, and then you can see exponentially this deviation, this error is being corrected, and after 10 periods or so, the error is completely eliminated. Okay, so that is due to the existence of the error correction model, which ensures that you don't go too far away from equilibrium. Any deviation from equilibrium is going to be temporary. It will eventually be eliminated. Now here we have a cross plot between x1 and x2. So x1 and x2, and because the cointegration vector is 1 minus 1, so x1 and x2, they lie around this 45-degree line, but of course there's a lot of wandering around this 45-degree line. But what this is telling us, what cointegration is telling us, is that the observations will never move too far away from the equilibrium defined by this straight line. Okay, so if you look at the last observation, it's far away from this straight line, and this information is useful because it tells us something about the future. Okay, if today we are far away from the equilibrium value represented by the straight line, because x1 and x2 are cointegrated, in the future we know that the next observation is more likely to be closer to the equilibrium line. Okay, so cointegration has implications for forecasting the future movements as well, because of the error correction component that tells us that in the future the error will gradually get eliminated. You will head back towards the equilibrium. So you get better forecasts based on these cointegration models. So if you were to make an out-of-sample forecast of the series for the future values, 101, 102, we would conjecture that xt would be drawn towards the equilibrium to close the gap. Okay, so now let's look at some examples how we can actually test for cointegration. Okay, so we've understood the theory behind it, but how do we test that cointegration actually exists? So we go back to the case of the orange market. Yeah, so here we saw that these are organic orange prices, regular orange prices. They seem to move together, and this is the difference between the two. Seems very stable and stationary. So it seems to us that they may be cointegrated, and we can look for an error correction model between these. So here, an estimated error correction model for organic oranges. Okay, so this is the constant, and then this is the error term for the last period, and this is the coefficient alpha 1. You can see it is highly significant. For regular oranges, constant term, not significant. This is alpha 2 also. Is it significant? Not significant, right? The coefficient alpha 2 is 0.008. This is much larger, right? So what is this telling us? Very good. Okay, so what these error correction models are telling us, because this coefficient is significant and negative, it's telling us that the organic orange prices are doing the error correction when there is a deviation from equilibrium. Okay, if you look at the regular oranges, this alpha 2 seems not to be significant, right? So that means all the error correction is being done in the market for organic oranges. Does that seem reasonable? So we have two markets. One is the market for organic oranges, one is the market for regular oranges. Which is the bigger market, do we expect? The regular one is the main market, And organic oranges is just a small niche market. So which one do we expect to affect the other one? Right? We expect that orange prices primarily determined in the regular market. And then the organic market adds some premium to that, 22, 23 cents. Okay? But most of the impact should be from there. So organic orange prices adjust to the error, and the regular prices do not adjust. That's what this is telling us. So organic orange prices seem to error correct very strongly, removing the entire disequilibrium each month. So these are monthly prices, and the coefficient is -1. So that means 100% of the error is eliminated within one period. The regular orange price, on the other hand, does not seem to error correct. The coefficient is negative, indicating a movement away from equilibrium. Okay, that's not a good thing. But the coefficient is small and it's really non-significant, so we don't really care. So simple interpretation is that the orange price is essentially determined on the large market for regular oranges. And organic oranges, they follow the price of regular oranges with an additional premium of 23 cents. Okay, so that's changes in the price of regular oranges are fully transmitted to the price of organic oranges after 1 month, while changes to the prices of organic oranges, they are not transmitted to the market for regular oranges. Okay, so now we move on to estimation and inference. Okay, so how can we estimate the unknown co-integrating vector beta, and how can we conduct inference? So Engel and Granger have a two-step model. So let's see how this two-step model works. So now we think of the regression formulation. So if x1, x2 are co-integrated, then we can write x1 in this way. So that's an equilibrium relationship. So, well, how do we estimate this beta 2 and mu? Well, we could just use OLS, okay? And that's the approach suggested in the original paper of Engel and Granger. So this regression is called a static regression. Static means all the terms are from the same time period. There is no dynamic structure, no lags, no leads, and things like that. Okay? So static means same time period. Now, Engel and Granger show that if x1 and x2 are I1 and co-integrated, then if you just estimate this model by OLS, the OLS estimator for beta 2 is consistent. Okay, so OLS is consistent if x1 and x2 are co-integrated. Okay, and what is interesting is even if the true model is different from this, okay, so we don't know what the true model is. The true model could be different from this. Okay, so it turns out even then beta 2 will still be consistent even if this model is misspecified, as long as the misspecification only relates to stationary terms. So two things we learn here. First is if x1 and x2 are co-integrated, OLS is consistent. Okay? Not only is it consistent, it is kind of super consistent. So even if this model is not correctly specified, that means it is missing a few other variables, even then OLS will be consistent as long as the missing variables are stationary. Okay, so that is important, because in the real world we don't know what the true model is. Okay, cointegration tells us now. So this is a big difference. In the stationary case, if x1 and x2 are stationary and we omit some other relevant variables, will OLS give us consistent estimate of beta 2? Yes or no? They're stationary, that means they're I0. Suppose this is the true model. So x1, x2, and w, they are all stationary variables. This is the true model, and I estimate okay, so the model that I'm estimating is misspecified. Okay, w is a relevant variable, but I don't know about it. Okay, I don't know the full truth, so I just estimate this model. W is missing. Okay, question is, will OLS be consistent for beta 2? Yes or no? Yes. Really? If you omit a relevant variable, then OLS will not be consistent in general. Okay? But now suppose x1 and x2 are I1 and they are co-integrated. W is I0. It's stationary. Okay? And then we are estimating so again, this is misspecified. There is no W here. So even if we miss some variable, our estimated model is misspecified, beta 2 hat will still be consistent as long as the missing portions are stationary. And the reason for that is that when we have I1 variables, then the stationary variables are too unimportant. They're just overwhelmed by the strong non-stationary variables. So even if we leave W out, it doesn't affect the estimates asymptotically. Okay, so OLS is still consistent. Okay, so the reason for that is the stochastic trends will dominate asymptotically. So for a large sample size, any misspecification of stationary terms will not affect the estimator. So that's one difference with the stationary case. Another difference with the stationary case is the speed with which the estimator converges to the true value. Okay, so consistency means that beta 2 hat converges to beta 2 as the sample size becomes larger and larger. And the non-stationarity affects the speed of convergence. Okay, so what does that mean? Now first consider the stationary case. So x1, x2 are stationary. Then we know that beta 2 hat minus beta 2, it will converge scaled by square root of t. It converges to a normal distribution with a zero mean and some variance covariance matrix V. So the speed of convergence here, okay, now we know that the variance, this variance covariance matrix, as t becomes larger and larger, the variance becomes smaller and smaller. It's going to zero asymptotically. Okay, but here the speed at which it is going to zero is going to be, we have square root of t, so the square of that is t. So it's going, the variance is going to zero at a rate of t. Okay? So the interpretation is the variance of beta 2 hat is t inverse v. So that's approaching zero at the rate 1 over t. So for the standard case, for the stationary case. But for co-integrated I1 series, the variance approaches zero at a much faster rate, 1 over t squared. Okay? So that is called super consistency of the OLS estimator. So to illustrate this, figure 3 has two graphs, A and B. They show the distributions of beta 2 hat of a true value of beta 2 equals 1. Okay, so the true value is 1, and in graph A, x2 is an IID variable, x1 is x2 plus an error term. So that's why the coefficient should be 1, the true value. And in graph B, the same setup, but x2 is generated as I1 as a random walk, and x1 will be x2 plus an IID error term. So in both cases, the true value is equal to 1. So distribution of estimators, the stationary case, is as you increase the sample size, you can see the distribution becomes narrower and narrower. All three are centered around the true value. Okay, and this. But if you look at the co-integrated case, you can see the distribution is much sharper. The tail is very small. So the variance of this is becoming zero at a much faster rate compared to the stationary case. So that is the phenomenon of super consistency. So the specification of the stationary terms is not important asymptotically. That means even if you ignore the stationary terms, if your sample is large enough, it's not going to matter very much. Okay? So that is an important advantage of cointegration. You can forget about a lot of things because, for example, if you're looking at consumption, we know that income is important, wealth is important. There could be many other things that are important. Okay? Right? Your mood, whether it is raining, whether it's cloudy day or a sunny day, hundreds of things could affect your consumption. Okay? And you can't include all of those in your regression model. So what this is saying is if you have a big enough sample and if you have a big enough sample, then asymptotically it's not going to matter if you left out hundreds of stationary variables that could have made a difference. Okay? But in small samples, in finite samples, it could make a difference. Okay? So asymptotically it's fine, but in small samples the OLS estimator could be biased in finite samples. So now in cointegration analysis, the static regression 7 is sometimes referred to as the first step of an Engel-Granger two-step procedure. Okay, so first step is we estimate a static regression like this, and then the second step is you estimate an error correction model. Okay, so that is the second step. The second step is a description of the dynamic adjustment towards equilibrium. And given the estimated cointegration parameters, so in the first step, we get the estimated cointegration parameters, beta 2, and mu, we get this from OLS, and then we can define the error correction term as the deviation from equilibrium, so that's our estimate of the error term. And under cointegration, this error term is stationary, and because the estimators converge to their true values very fast, super consistency, we can include the error of the previous period, the error term, as a fixed regressor in a dynamic model. Okay, so this is the error correction term. So you can estimate this some stationary model, right? So the change in x1 depends on the lag of the change in x1, depends on the change in x2 today, lag of the change in x2, and this error term. Okay, so here notice that all the terms are stationary. So you could just include enough lags to make sure that this epsilon is a white noise process. Okay? So all the terms here are stationary, so you can use the standard inference procedures for these parameters. Okay, and the t ratios follow normal distribution asymptotically. Okay. Now normally you cannot have ut minus 1 hat as a regressor. Okay, so this is called a generated regressor because we don't observe the true value of ut minus 1. It has to be estimated from this. And in the normal case, if you put in a variable which is generated from another regression, that introduces a bias in the regression. But here, we can include ut minus 1 hat as a regressor because of the very rapid convergence in the first step to the true value of beta 2. Okay, so that's what we are saying. Okay, so that's how an error correction model is estimated. But notice all of this analysis is conditional on the fact it's only if x1 and x2 cointegrate, then you can estimate this regression. then you get the error term, then you estimate the error correction model. But the first thing is to test whether x1 and x2 are co-integrated. Okay, and that's what we will do next. Okay, we have only 5 minutes, so I'm not going to start a new topic now. So let's stop here for today. And next week, of course, we don't have a class, so I will see you in 2 weeks. Okay, have a good holiday.
没有作业。但是他在干嘛？但是这节课在说什么？我怎么觉得推翻了我前面学的东西呢？没有推翻上节课的东西，怎么？每节课都是这样子。啊，这。